In this question, we're given some measurements of the initial rate, and then we're asked to determine the rate law and the value of k from this information. So if you want to determine the rate law for something, and you're given information like this, you want to look at the ratio of the concentrations when they change versus the rates when the concentrations are changed. So we want to take the concentrations over here and the rates over here, and we want to take a ratio and compare them. So let's just think about this. If we double the concentration and it doubles the rate, then we know it's first order. If we double the concentration and it makes the rate go up by 4 times, we know it's second order. If we double the concentration and it makes the rate go up by 8 times, then we know it's third order, so on and so on and so on. So let's look at these relationships. First, just because this is the order they come in, if I look at the trial 1, if you will, versus trial 2 in the middle, let's see what's changed and what hasn't. The nitrogen concentration has remained constant, so therefore we know it will not affect the rate because it's constant. But the hydrogen concentration went from 1.49 to 7.44. Now, I like to put the larger number on the top, but it doesn't really matter. So I'm going to put the 7.44 on the top, and I'm going to put the 1.49 on the bottom, so I get a whole number. And when you do that, you find that it's 4.993. Now we have to do the same things with the rates. We want to put the larger rate on the top because it corresponds with the 7.44, 265, and the smaller rate on the bottom, 53. And when you do that, it equals 5. Well, 4.993 is approximately 5. So this means we've increased the concentration 5-fold, and the rate has gone up 5-fold. That means with respect to hydrogen, whose concentration changed, notice nitrogen's concentration was constant, so therefore it's not a factor in this particular example. We know that if hydrogen goes up 5 times, the rate goes up 5 times, so it's first order with respect to hydrogen. So we can start rate equals K, concentration hydrogen to the 1, but if it's to the 1, we don't write it. I missed the diatomic hydrogen there. Let's do the same thing for nitrogen. And if we look at nitrogen, we have to compare number 3 with number 1. Because here, the concentration of hydrogen remained constant. You wouldn't want to compare these two, because if you compare these two, both things change. So compare where hydrogen stays constant, in this case at 1.49 molar. Said another way, compare the first trial with the third trial. So again, I like to put the bigger number on top. So I want to put the 0.82 on top, the smaller number on the bottom, 0.39. And when you do that math, you get about 2.1. Now, for the rates, I want to put the 53, larger one on the top, and put the 12, the smaller one on the bottom, and I get 4.42. Well, to convert 2.1 into 4.22, 4.42, you have to square it. Said another way, if you took the square root of that, you would get this. So if I essentially double, or 2.1 times the concentration, I get 4.42, or essentially 4 times the rate. So it's second order with respect to nitrogen, which is concentration of N2, which is squared. So now I have my rate law. Now to find my rate constant, I just want to plug in any of the values. It makes no difference, but I'm going to use the first one. Don't jump across. Don't pick this one, and this one. Just stay consistent. So I'm going to use these values. So my rate is 53.0 molarity per second equals K, concentration of hydrogen is 1.49 molar, and then concentration of nitrogen is 0.82 molar squared. So I want to take care of this side first. So I'm just going to rewrite this, 53.0 m per second. I'm just going to move this up so you can see it, equals K, and then 1.49 times 0.82 squared, which comes out to be 1.001876 m cubed, because there's an m here and an m squared here. And I care about 2 sig figs because this is 2 sig figs. Now divide both sides by this number, 1.001876. Polarity cubed, that cancels. And over here, 1.001876, polarity cubed. K equals, 1 molarity cancels out, I'm left with molarity squared on the bottom, and seconds on the bottom, 52.901, 1 over m squared s. Again, I had m on the top and 3 m's on the bottom, so that goes to 2. And then I have m squared s on the bottom, like this. However, I need this as 2 significant figures. So k equals 53, and probably Alex wants this as m2 minus s minus 1, or just minus, like that. So this is the same thing. 1 over m squared s is the same as m to the minus 2 s to the minus 1, or just s minus. One thing to point out, if you notice, this is exactly the same number as the initial rate of the reaction. That is purely a coincidence. Sorry, you can't really see that. The initial rate of the reaction was 53, and k is 53. That is purely a coincidence. They don't have to be the same.